In the last few discussions, we discussed about CTAT, and we said we derived that if you pass a constant current through a diode, the voltage across is a CTAT. And we found the dependence of temperature, that is dou CTAT by dou T is approximately equal to minus 1.6 millivolt per degree Kelvin. And then we discussed PTAT also, and we derived the PTAT with this type of circuit. R2 is R1. We have n number of diodes here in parallel, and we connected this so that the same current flows through all the branches. And we said this voltage is a PTAT. And we found the dou by dou T of PTAT is equal to, that is dou by dou T of Vt is equal to near to 85 microvolt per degree Kelvin. So we got voltage across the diode as a CTAT, and voltage across a resistor as a PTAT. And to get a reference, we said V reference equal to get a reference value, we had to add PTAT and CTAT. And the alpha 1 and alpha 2, we will come to that point a little bit later. Now I am thinking on the circuit point of view. How we will adjust PTAT and CTAT, we will discuss little bit later. So we want to add two voltage sources, PTAT plus CTAT, and we have one voltage reference CTAT here and another voltage source PTAT here. So if we have one voltage V1 and another voltage V2, how we will add them? Suppose we have a 2 volt here and we have a 3 volt here, and suppose I need 5 volt. How you can make a 5 volt? We can connect them in series. It's a 3 volt and it's a 2 volt to get a 5 volt output here. So this is equal to, this node equal to 2 volt per 3 volt. So if we connect two voltage source in series, that is V1 and V2, then we can easily get V1 plus V2. So similarly, we can connect the CTAT and the PTAT to form a PTAT plus CTAT, that is V reference. So here in this circuit, I have my PTAT here. This is the PTAT source, and I have my CTAT here, so that I can get a V reference here. So this potential is PTAT and this is CTAT. let us draw the complete circuit diagram. We have N diodes here. This is R1 and this is R2, and the voltage across R2 is a PTAT. Now I want to add my CTAT here, and we already saw how we will add the PTAT and CTAT. Now the circuit that I draw in red color is the PTAT circuit, and what I draw in the green is the CTAT. So voltage across this R2 is the PTAT, and voltage across this diode is a CTAT. And what we will get here is the reference voltage, that is V reference. That's the band gap output voltage. And we said a diode is implemented in the CMOS process as a PNP BJT, where the P and N are connected to the ground. So we can redraw this same circuit using the BJT, which will be more familiar to you. In almost all the textbooks, the BGR circuit is drawn using BJT. So let us modify this circuit. Only the modification is we are replacing the diodes with BJT. We have R1 here, R2 here, and this much is our PTAT circuit. Now we have our CTAT circuit, and here is the reference voltage. So this circuit, I think you all are familiar with this circuit, and in this circuit we have, instead of n diodes, we have n BJTs in parallel here. So this is the circuit that most textbooks will have, and now we will discuss how we will adjust R alpha 1 and alpha 2 to cancel the CTAT and PTAT correctly, so that when we add alpha 1 PTAT plus alpha 2 CTAT, we will get a constant voltage, a reference voltage. So far in the discussion, we designed our PTAT and we designed our CTAT, and we added our PTAT and CTAT together to form a reference voltage. But there are some issues that we didn't address till now. Clearly speaking, there are three issues that we have to discuss. The first one is the supply variation. In the beginning of the discussion, about the BGR reference, we said there are two things that we should take care. First one is the variation of output voltage with respect to temperature. Second thing is the variation of the output voltage because of the supply variation. But till now we didn't address this issue, the supply variation. So we have to discuss the supply variation. And second thing, when we designed our PTAT and we designed our CTAT independently, and then we added them together uh, to form this circuit. But there is one issue in this circuit. The issue is that when we designed our CTAT, we said voltage across a diode is a CTAT when a constant current is passed through the diode. So we did the simulation also. We did the simulation for CTAT by passing a constant current through the diode. But the current which is flowing through this resistor, in this circuit, the current which is flowing through the resistor is also flowing through the diode. So this current is not a constant. So we already derived the expression for the current, and it is clear that it is not a constant. So in one of our previous slide, when we derived the expression across the voltage, expression for voltage across this resistor R, and later we called it as R1, then we found the expression is I0 into R1 equal to Vd minus Vd1, that is equal to Vt into ln n. So clearly it is a PTAT, because ln n is a constant but Vt is PTAT. So I0 R1 is a PTAT. Then we derived the expression for our current I0, that I0 equal to Vt into ln n divided by R1. So in this expression also, I0 is a PTAT, and we've said that because of this current mirror, I0 will be flowing through all these branches. So I0 equal to Vt by R1 into ln n. So ln n is a constant. We already said that n is the number of diodes we have in parallel, and R1 is a resistor, and R1, the resistor will depend on little bit on temperature, but it is not very much. We can ignore that dependency, and Vt is a strong PTAT. So I0 is a PTAT current, but our assumption was the current which is passing through the diode to form a CTAT was a constant current. But what we did, we connected a diode here, and we said voltage across will be CTAT. but our initial assumption was to pass a constant current through the diode. So that is another problem that we need to discuss. The third problem, the third topic that we didn't discuss till now is about alpha 1 and alpha 2. So the second issue that we need to discuss is the current through diode. So initially we assumed it as constant, but when we design the circuit, the current which is passing through the diode is PTAT in nature. So what is the effect of that and how much it is affecting? Is it really affecting our CTAT? Those things we will discuss in the next topic. And in the third one is alpha 1 and alpha 2. So we said alpha 1 and alpha 2 are required in our expression so that the PTAT and CTAT get cancels completely. So we will adjust alpha 1 and alpha 2 to completely cancel the CTAT and PTAT. But when we design our circuit, when we design our bandgap reference, we simply added the PTAT voltage and CTAT voltage. Till now we didn't discuss about alpha 1 and alpha 2. So the third thing remaining in the BGR reference design is to find what is alpha 1 and what is alpha 2, and we adjust alpha 1 and alpha 2 so that PTAT and CTAT nature get cancels completely. We will start our discussion with the first point, that is supply variation. So let's discuss about the supply variation. Initially, when we started the discussion of BGR reference, we said we should take care of the supply variation and our reference voltage should not vary with the supply voltage. But later on in our discussion, we didn't mention anything about the supply variation. So how the supply variation is being eliminated and how the effect of supply is eliminated in our circuit, that we will explain now. So when we were designing our PTAT circuit, we said we developed our PTAT with one diode, and then we had some number of diodes in parallel. We had n diodes in parallel, and then to get the difference between this voltage Vd and this voltage Vd1, to get the difference between these two voltages, we put a resistor R, and we said somehow we will make these two potential equal. We call that voltage as V2. So this is what we did. We said we will make some circuit here to make Vd equal to V2. If we are able to make Vd equal to V2, then the voltage across the resistor R is a PTAT. So this circuit is very important. So this circuit what we are using here, we said it can be of two types. One is of current mirror type. The second thing is circuit using op-amp. And we are applying our supply voltage here. So this is the supply. So in circuit point of view, the supply variation is rejected by this circuit. Whether it is a current mirror or it is an op-amp circuit, it doesn't matter. It is the duty of this circuit to eliminate the effect of supply variation. So if you design some circuit to ensure that Vd equal to V2, it should ensure that Vd equal to V2 even if supply variation is present in the system. So how good is our current mirror, or how good is our op-amp's arrangement to make Vd equal to V2? It will automatically will be robust to supply variation. So we need not design any separate circuit for supply variation in bandgap reference. I am repeating, the circuit which we use to make Vd equal to V2, it is the duty of that circuit to reject any supply variation in the circuit. So we should be very careful when we design our current mirror or our op-amp based design to ensure these two voltages to equal. And when we designing this circuit, we should make sure that that circuit is capable enough, that circuit is good enough to remove all the supply variation also. So we will do this, we will come back to this point when we do the simulation of the BGR, and we will simulate the BGR with different kind of current mirror and different type of op-amp structure. So it will be more clear when we do the simulation. So let us move to our second point, that is the current through the diode. So when we started the discussion of CTAT, we said we will pass a constant current to a diode, and the voltage which is developed across the diode Vd is a CTAT in nature. And finally, when we made the BGR, we added the PTAT voltage and the CTAT voltage to form the BGR. But when we added that, so we've said that resistor, the voltage across that PTAT resistor is PTAT in nature, and then we added the diode here. So it is this circuit I am referring to. This voltage across the resistor is PTAT, and this is our diode. And we said we will get a reference voltage here if this is PTAT and this is CTAT. But the current through this diode we found, that is I0 equal to Vt ln n divided by R. It is not this resistor, it is actually this resistor. So it is actually this resistor R1, so we call it as R1. So here is the issue, that when we developed the CTAT, we said the current is independent of temperature, that is, the current is a constant. That was our theory. Then when we designed the circuit of BGR, the current which is actually passing through the diode is a PTAT in nature. It is a PTAT current. So what is the effect of that? So clearly there will be some difference in our CTAT nature. So now we should calculate how much our CTAT varying from our initial derivation and those things, and how much the slope of the CTAT is varying when the PTAT is passed through the diode instead of a constant current. So we set the voltage across the diode Vd. We said it is Vt into ln I0 by Is. This is where we started the discussion, and we said the Vt is a PTAT, but it is very weak, and since the I0 is very much dependent on the temperature, and we said Is is very much dependent on temperature, and Is increases with respect to temperature, and initially we said I0 is a constant. So because of the Is, this term is a strong CTAT and this is a weak PTAT. So the entire effect, effectively it formed a CTAT curve. But now the difference is that everything is same. Vt is same, it is a weak PTAT, and is is again the same. We already derived the expression for is, and we found dou is by dou t also we found. The only difference is that instead of I0 is a constant, now I0 is a PTAT. So when we analyze the CTAT voltage, we found the expression for Vd, and then we found the expression for Vt, the thermal voltage, and then we found the expression for Is. Then we found dou Vd by dou t, that is how much the diode voltage changes with respect to temperature. To get that expression, we found dou Vt by dou t, that is how much thermal voltage is changing with respect to temperature. And then we found dou Is by dou t, that is how much Is is varying with respect to temperature. And dou I0 by dou t, in that derivation we took it as 0. That because our assumption was I0, that is diode current through the diode, is constant with respect to temperature. So that assumption is wrong when we come to the circuit. So we have to derive the expression for dou Vd by dou t to get the correct slope, and we have to see how does it really affecting our CTAT circuit or not. If it is really affecting our CTAT circuit, then it is very much considerable. Otherwise, if it is not affecting very much, then we can neglect the effect of that CTAT current. We can say that even instead of constant current, even a PTAT current is passed through a diode, we will get a CTAT voltage. So we have to find how much it is affecting in the slope of the CTAT. So to find that, we have to find dou Vd by dou t. So dou Vd by dou t equal to dou by dou t of Vt into ln I0 by Is. Here Vt is dependent on temperature, I0 is also dependent on temperature, Is is also dependent on temperature. So the differentiation will be a little bit complicated. So to make the differentiation easy, I am writing it as dou by dou t of Vt into ln I0 minus ln Is. We know ln A by B we can write as ln A minus ln B. So the ratio is removed and it is subtraction now. So it is easy to differentiate. So again, it is a product rule. It is the first term is Vt. So this is the first term I am considering, and this is the second term. So the rule that we follow is first term into derivative of second plus second term into derivative of first. So we can write dou Vd by dou t equal to first term is Vt into derivative of second term is 1 by I0 into dou I0 by dou t. Initially we assumed dou I0 by dou t is 0, but now that it is not the case, now we saw I0 is varying with respect to temperature and it is a PTAT, minus 1 by Is into dou Is by dou t. So first term is over. So first function into differential of second plus second function is ln I0 minus ln Is into differential of first is dou Vt by dou t. So in these two expression, expression for Vt we already know. Expression for Dou is by dou t, we already derived that. It is in from the equation 4. We will get dou is by dou t. In this expression, Vt, dou is by dou t, dou Vt by dou t is known to us. We already derived those expressions. So the only thing which is remaining is dou I0 by dou t that we have to find. So the expression of I0, that is the current through the branches of the current mirror, that equal to ln n divided by R1 into Vt, where n is the number of diodes in parallel and R1 is the resistor across which we got the PTAT voltage, that is this resistor R1. So the current through these branches is equal to, that is I0 is equal to ln n into Vt divided by R1. So the same current will flow through this branch also, and the same current will flow through our diode, which should act as a CTAT. We already derived this expression for the current. If you have any doubt, you can go back to our discussion on PTAT and you can find this expression there. In this expression, that is I0 equal to ln n divided by R1 into Vt. So dou I0 by dou t is equal to, we have to differentiate this term. So strictly speaking, resistance, that is R1, is also dependent on temperature, but the effect of that dependency is very small, and for the time being we can neglect that dependency. So I am assuming R1 as a constant and ln n is also a constant. So ln n divided by R1 into dou Vt by dou t. So that equal to ln n divided by R1 into dou Vt by dou t, that we know it is dou by dou t of Kt by Q. And now we can write dou I0 by dou t is equal to ln n divided by R1 into K by Q. So this K by Q, again we can write it as Vt by T. So that equal to, now we can write dou I0 by dou T is equal to ln n divided by R1 into Vt by T. Now again this term, that is ln n into Vt divided by R1, that is the expression for the I0 itself. So now we can write dou I0 by dou T is equal to I0 by T. So we differentiated this expression and we end up with this expression, and we found that ln n divided by R1 into Vt is exactly the same as that the expression for I0. Then we can write expression for dou I0 by dou T. So this is the final expression for dou I0 by dou T. So from the expression 4 that we derived earlier, this is one of our earlier slide. So we have dou is by dou t. So I am just rewriting that expression, that is dou is by dou t is equal to is into 4 plus m divided by t plus eg by kt square. We already derived this in expression number 4. And we have dou Vt by dou t, that is equal to K by Q, that is equal to Vt by T. I think it was our expression 2 or 3. I don't remember exactly which was it. You can check that. Now we got all these three relation, that is dou I0 by dou t, dou is by dou t, and dou vt by dou t. Now we can find what is dou vd by dou t, that is how the rate of, that is the voltage across the diode. So here we derived that dou vd by dou t. So to find the exact value we need dou I0 by dou t, dou is by dou t, and dou vt by dou t. And now we got all these values. Then now we can proceed from here. That is dou vd by dou t is equal to vt into 1 by I0 into dou I0 by dou t. So the dou I0 by dou t is equal to I0 by t, that we derived. So I am writing I0 by t minus 1 by is into dou is by dou t. So the dou is by dou t we got from expression 4, that is equal to is into 4 plus m divided by t plus eg by kt square. So I am writing it also, that is is into 4 plus m divided by t plus eg by kt square. So we have the first term now. The second term we have ln I0 minus ln is into dou vt by dou t. Dou vt by dou t also we derived. So that is vt by t or k by q. So we are writing vt by t here. It is vt by t. A lot of simplification is possible here. Like we can cancel this I0 and I0, this is and this is also we can cancel, and that is equal to vt into 1 by t minus 4 plus m divided by t minus eg by kt square plus, we have a plus here, plus vt by t into this term ln I0 by ln I0 minus ln is, we can write ln I0 by is. So now if you check vt into ln I0 by is, it is the expression for Vd, that is voltage across the diode. So now we can write as the dou Vd by dou t is equal to Vt into, here I am taking t as a common, so 1 minus 4 plus m minus eg by kt square plus vd by t, because vt into ln I0 by is we replaced with vd, that is equal to you can write, I am bringing this term to first, so vd by t minus this vt into minus 4 plus m minus 1 into vt by t minus vt into eg by kt square. That is equal to vd by t minus 3 plus m into vt divided by t minus this vt I can write kt by q, then eg by kt square. So here also we can cancel 1 kT and 1 kT, 1 T will remain here. Now dou Vd by dou T, we can write Vd minus 3 plus m into Vt minus Eg by Q all divided by T. So this is the slope of the CTAT when we consider I0 as a PTAT. Earlier we derived the dou Vd by dou T, that is slope of our CTAT, considering I0 is a constant. So now we have two expressions for dou Vd by dou T, one with I0 considering as constant, one with I0 considering as a PTAT, which is really happening in the BGR circuit. Now let us compare these two expressions and see how much is the effect of that PTAT current and how much it is affecting our CTAT. So by considering I0 as a PTAT, we got this expression, that is I0 is a PTAT. And earlier we derived this expression in the slide. This is our previous slide, that it gives dou Vd by dou T equal to Vt minus 4 plus m into Vt minus Eg by Q. So this is our previous slide considering I0 is constant. So by comparing these two equations, the only difference among the two is here it was 4, here it was Vd minus 4 plus m into Vt, but here it is Vd minus 3 plus m into Vt. So the difference is that 4 became 3. When we substitute the numerical value, here it comes 4 minus 3 by 2. Now it will become 3 minus 3 by 2. Let's substitute the values. So dou Vd by dou T, assume Vd is 0.7 minus 3 minus m is minus 3 by 2, that is 1.5, minus Eg by Q is 1.2, that is 1.2 electron volt divided by Q, that is 1.2 itself, all divided by 300 Kelvin. Oh, we missed the Vt value here, that is equal to 0.7 minus 3 minus 1.5 into Vt is 26 millivolt minus 1.2 all divided by 300, that is equal to now I am finding only the middle term, because that is the only term that changed from the previous. Instead of 3 it was 4, now it is 3. So it is 3 minus 1.5 into 26 millivolt, that is equal to 39, that is equal to 39 millivolt now. So 0.7 minus 39 millivolt minus 1.2 all divided by 300, that is equal to 0.7 minus 39 milli minus 1.2 divided by 300, that is equal to minus 1.79 millivolt per degree Kelvin. So this minus sign indicates that when the temperature increases, slope voltage decreases. Minus sign indicates that the slope is negative, that means when the temperature increases, the voltage decreases, that negative slope. So still it is a PTAT. That means even if the current through the diode is PTAT, the voltage across the diode is CTAT. And when we compare with our previous value, so let us compare with our previous value. So that is here. Uh, the expressions in red, this color is our previous value, and the green is our new value. And green is when we consider I0 as a PTAT, and the red color expressions and this thing when we considered I0 is a constant. So here 0.7 minus 65 millivolt minus 1.2 came. So here when we consider I0 is a PTAT, it is 0.7 minus 39 millivolt minus 1.2. So when we derived this expression itself, we said the middle term don't have much significance because that is in millivolt. And here also the difference is only in the middle term, so there is only some millivolt range of difference. And here the slope we got it as minus 1.88 millivolt. Here the slope we got minus 1.79 millivolt. So there is not very much difference even if the current is a PTAT. So our conclusion in this discussion is, initially we assumed I0, that is the current through the diode, is a constant, and we derived the expression for dou Vd by dou t, and we found it is minus 1.88 something. That really depends on the voltage across the diode, that is the Vd term, and in the textbooks that was given minus 1.6 millivolt per degree Kelvin. Then when we made the circuit of the BGR, we found that actually the current through the diode is not a constant, it is a PTAT, and then we modified all our equations assuming I0 is a PTAT. Then we found the slope of the CTAT curve, and our summary of this discussion is, even if I0 is a PTAT, the voltage across the diode is CTAT in nature, and the slope is near to 1.79 millivolt. And this is not a very correct value. This value very much depends on the Vd, that is voltage across the diode. So if you consider voltage across the diode is 0.7, then you will get one value of the slope. If you consider the voltage across the diode as 0.75 or 0.8, then this value will vary. So we can ensure the value only after the simulation, how much Vd is coming. And this slope, again we said this slope is dependent on the temperature, so you will not get a constant slope. The slope itself is dependent on the temperature. So now our second point is also over. Even if the current passing through the diode is a PTAT current, still we will get a constant, still we will get a CTAT voltage across the diode. So we are safe, we can use the diode as a CTAT voltage source. Now let us come to our third point, that is design of alpha 1 and alpha 2.